Alright, in this video we want to look at the relationships that exist when we have a tangent that intersects with a secant line. So this line is tangent, it intersects at one particular point called the point of tangency, and if we were wherever this radius happens to be, that looks like it's about the center. If I were to draw a line that is a radius, and that's not my best line, but you guys get the picture, it would be a right angle. Okay, so this line is tangent, this line is secant. What we want to look at is what are the relationships that exist. So let's get that stuff off of there. First thing we want to look at is the relationship that exists between the lengths of these particular lines. So in order to do that, what I'm going to do is I'm going to add in this little, basically just add in this guy right here, and I'm going to connect these points on the circle as well, which allows us to create two triangles. Okay, if you remember back to our original picture, all we had was ABC and AD. That was my tangent line. ABC or AC, however you want to say that, was my secant line. It intersects it at 2 points, and we want to figure out a relationship between the sides. So we want to prove that these are similar, and we're going to do this very similar to how we did it before. There's one little point that may be a little bit obscure, so let's go ahead and do this. So number one of my proof, let the diagram be given. So in this particular scenario, let AC be a secant, and it intersects with the tangent AD at the circle in the manner that's given. So similarity proof again, let's use AA if we can. Number one, angle A is going to be shared between these two, so that's the easy argument. So again, two different ways you can do this. Measure of angle A equals measure of angle A by the reflexive property, or a little bit less technical, we can just say that angle A is a shared angle, so it's congruent to itself. The other angle argument is a little bit more obscure, so let's check out what's going on down here. Number one, I need to make sure that I match up corresponding parts because they're not necessarily readily recognizable here. So let's look at ADB first. So ADB, the measure of angle ADB. We need to match that up with its corresponding angle, so we want ADB. That means we got to go ACD in the order there, and we need to show that these two are congruent. How we show those two are congruent is very similar to the other videos that we did. These are actually, we're going to argue that these are inscribed angles. So inscribed angles project to, they have a vertex on the circle. So does that satisfy that? Absolutely, there's the vertex. And the arc that it subtends is between the two endpoints. Okay? So not your traditional inscribed angle, kind of like this one is. This is your traditional inscribed angle. But what happens is it creates this arc. It's an inscribed angle. So it creates this arc. But let's look up here at angle ACD right here. Maybe I should mark these with 2 so we don't get confused. I've already got angle A marked with 1. But angle ACD is an inscribed angle, and it projects to the same two endpoints, and therefore subtends the same arc. So it's the same exact argument as before. It's just not as traditional, quote unquote, of an inscribed angle. It's a tangent, but it's still inscribed because it has a vertex on the circle, and therefore these two are congruent. They must be congruent because they are inscribed angles. So we're going to say since inscribed angles that project or subtend the same arc must be congruent. So what did we just show? Well, what we just showed is that these two triangles are similar. So by AA, we know that triangle ABC must be similar to triangle ABD. because of that, we can write some relationships that we know. So let's carefully write those side relationships, or the ratios of sides. Remember, BD we just kind of introduced in order to do the proof, and so that's not going to be one that we argue. So BD and DC are definitely, their ratio is going to be the same as the other ratios, but that's not necessarily what we started with. Remember, we started with the scenario where we just had the tangent line and this particular secant line. All right, so the other ratios that we have then are AB. We start in this red triangle. AB is going to match up with AD. AB, that's the shortest side in the red triangle, will correspond with the shortest side in the blue triangle, and so that ratio is going to be equal to any other ratio of corresponding sides. The other ratio that we're interested in is AD in the red triangle. Now, because we started with the larger triangle, the smaller triangle, we need to start with the side in the smaller triangle. So the side in the smaller triangle is going to be AD. And that matches up with, in the blue triangle, AC. Well, it's interesting what happens here. We've got two of the same variable. And so we've got this proportion. You can absolutely use that proportion to write the ratios of the sides. But when we cross multiply, look at what happens. We see that AD, which, if you remember, that's the tangent line. That's the length of this line that's tangent from the intersection of the tangent and the secant to the point of tangency. It's that value squared is equal to the exterior piece here, or the part of the secant, times the entire secant. So we see this thing of kind of part times whole repeating in some of these things, and so this is the relationship that we really want to use. If we recognize that AD is the length of the segment from the intersection of the tangent and the secant and the point of tangency, then that value squared will equal the product of the part of the secant that's exterior times the whole. So I remember this as tangent squared, and again, this is that whole idea of exterior part times the whole. So the last thing we need to talk about with regard to this tangent-secant relationship here is what angle relationships are present when we have this situation. So let's go ahead and take our diagram and move it up a little bit so we can get everything in the same frame here. But so what essentially happens is this relates directly to that secant intersection, in that the angle on the exterior is going to, when you get this intersection, it's going to create two arcs technically. So the first arc would be arc BD, which is smaller, and the larger of the two arcs that are created when this passes through the circle is this arc here, arc CD. So we have these two arcs that are created, and they're related to the angle in a much similar way to the secant-secant relationship, in that the measure of angle A, and we'll just call it angle A here, that's the angle on the exterior, is equal to half the distance of the two arcs that are created by the intersection. So we look at the larger arc, it's always the larger arc, which is CD, and we're going to subtract from that the smaller arc, so the difference between the two arcs, and we're going to divide that by 2 in order to find the measure of angle A.